very much associated with linguistic terms, so statements like large, small, fast, quick, big, small, that type of terms, which are linguistic terms, but Hazlitt allowed us to understand that type of statements, that type of terms in a more mathematical way, in which we do some calculations and representation of these terms in the form of a function. There's also the aspect of precision, and that's kind of associated with linguistic terms which I just mentioned, like short or short, fast or slow, and again, is something we can always precise statements. And it's not easy. You see that even with the names indicates that maybe it's not very precise, fuzzy, but it would be very simple and immediately grasp the idea of the process. So, just a word of applications that we see consonants emerging more and more in different places. We think that as highly applicable. It started very much with the studies of communication systems, and there was a lot of ideas about sensors and some input information that you can use to precise, but also what is really interesting when you don't need to something in sense of a decision, some type of output, and control. So that kind of is always has to be precise. So it's not only the precision, but also it always need to have precise inputs. The issue of moving things will always belong to the less non-things, like some kind of areas which we have to treat. There's also the aspect of decision making, that's when multiple individuals trying to get some kind of consensus about specific economy, or one disabilities, and have that university form, fuse and eventually combine some outcome is also unbelievable and difficult, because once they human model is and all that type of things regarding the classification, the computation, characteristics, anything which is imprecise and also does not mean or does not provide yourself. So after that, after that, let me start talking about the essence of the learning in the process. So because we can look by what is happening, so about 60 years, and the purpose of that was to describe the music. So the concepts which we know explicitly identified as ways of thought, something which is structured as the brain is something that was between which means there's no or true thoughts. That was sort of the principle behind the concepts. So before we start, I will kind of show ourselves quickly in the section so far. Let's talk a little about the crystals. So in this case, the crystal is something like we already know, like elements belong or not belong to this. So if we envision that we have this, if we envision that we have a set of the temperatures from 0 to 15 degrees, which represent the set of temperatures which we would call cool. And then we have another set of temperatures, 15, let's say here, 25, which represents the nice temperature and anything above 25, we will identify as cool. So that means that when we think about the temperatures that we have a few sets, cool, nice, and hot. Then if you have temperature, for example, 15, we will assign that temperature to the set, which we label as. The problem here is such that if we have temperatures around 50, let's say 40 millimeters, and 50 is cool, so very close to this border between cool and nice, then just a very small difference in temperature jumps us to one step forward. That is where the fuzziness comes into place. And this is where the concept of fuzziness comes, that we do not have always a full membership of, in this type of case, temperature of the organism. So what we have is that we have, here we have this, maybe the second, this represents the degree to which an element belongs to. So you see here one, that means that all of these temperatures from 0 to 15 belong to the second. And 15 to 5.9 and above 5. So the first is we have below meter. So not all temperatures belong in the same degree to the size. And then, as you can see, the border is really fast. So let me just give an example. If we have any temperature between 0 to 10 degrees, you see that the membership of that temperature in the set group is still up. But any temperatures that we have between 10 and 15, this line here represents value. If, for example, take a temperature 15 and you look at this point here, which crosses with the line decreasing will indicate that this temperature will be known to this temperature, so you will be able to see at the same time, the same temperature 15, if you go across that line vertical, the percentage temperature will be shade representing the set nice, it belongs to the degree of instance. So that means that these temperatures in this range, they, if you go from 10 to 18, they decrease their membership in the set group, and they increase their membership in the same class. So in this particular case, this region start at the temperature belong to the Scandinavian set, 4 nice, and further we go in the direction they go more to one and they increase the level, and if you go from the higher to the lower, you go to the higher direction. So that is the essence of the process. So the membership is not just 0 to 1, it is between 0 and 1. So if you go just to the example, if you go back to the crystal size, then we have the temperature of 3, 18, 23, 25. Now all belongs to the gas. And this 3 belongs to the. So that means that there's only ability to say yes or no. Yes, these temperatures belong to them. Stabilize, these temperatures belong to the same cool, but not to the ice. In case of the fuzzy, it's the same type of thing. If we have the same temperatures, then we have a degree to reach this temperature belong to the ice. So in this case, with the children, we are not concerned about the same ice. This is just a mathematical expression which defines as a function. And the temperature which is, let's say, 5 and 10 do not belong to the same place, but temperatures which, let's say, this 12 and 3, they belong to the degree. The first one is, let's say, 4, 6. Here, these two temperatures again belong fully to the same place. This temperature represents, let's say that it's 5. It belongs to nice and hot to the degree of 4. So it's really not nice to talk about something. That is the idea of science. We don't need to be very precise in describing the composition of language. So in other words, we have some concept, and the concept of temperature, and three, and description of the labels, food, nice and hot. You don't have to be very precise in describing what is happening. We have some which temperature was to a degree involved in substance. So that's kind of how we represent this. So we say that the temperature 5 or 10 equals 0, 12, 15 minus the exact values 25 and 65, 65 each 2, 18 and 23, 1, and 25. So that's the size. 71 species. Sometimes we have to function. We don't have to use those that we specify as a function. But often we use that for something which we might look for in membership. Because that represents the membership degree to which this point belong to the segments. And in this case, we have a formula for that, indicating that the values belong to 0, above 28.0, and then we have a flat scale value of 1, and then you can see that some kind of function which represents as 0, and this between 10 and 18, and then turns out to be 8. So that is another way how to represent the function. And quite often we use that when we build these systems. The shape of the functions could be variety, you could have a rectangular, trapezoidal, the S, the Z, some kind of names, but these are all possible functions which we can choose to identify to what degree elements belong to whatever the label we assign to that set or function, representing some kind of concept which we are interested in. So, having said that, that is the possible, and we already seen the 3 sets, fuzzy sets, which is full nice apart, with describing our perception, what does it mean to be cool, what does it mean to be nice, thought, and we can adjust it to our own needs and our own perception of how we can perceive it, how we perceive it. Could be about the car, for example, the age of the car, could be new or old, could be distance from the small far. Of course, in this particular case, our universal scores, in this particular case, our temperature, we can define any type of domain change. So, for example, in the case of the age, it could be years, in the case of the distance, it could be kilometers. And in this case, we identify what rate of values satisfy our membership to a given society. So having said that, the next kind of element which we can talk about after the short introduction to the fuzzy set is the relations. We all know relations that on the first part, we could say like the binary function is that the x is the y is a function of x. So that is a very useful application that we have 2 domains in our crystal. But we have also the fuzzy relation. So in this particular case, we talk a little bit about the framework of fuzzy logic. We talk about the proposition. So we had the domain, and we had a set, something that we just, for example, talked about in the case of introduction, like for example, temperature. And then we have a context set which models that we used. So, as you can see here, that is the plural form that we have some domain, and we talk about that specific linguistic term when we try to describe this fuzzy set which we produce last month. So, for example, temperature is nice, the age of the car is new. So, of course, the nice and new represent the concept which we use as a label for our fuzzy set. So we define the nice, what does it mean in temperature, we define what does new in the car, and we do not specify the number. Nice, for example, 18 degrees, and the new like a 1-year-old, we just put the new entries. And then the system will provide also the definition, what does it mean new, like nice, in the form of the fuzzy set, and the system knows something. Of course, you can put things together, so you can have a statement like this, and then in this particular case, you can have 2 different domains, 2 different fuzzy sets. So, for example, the things which we had before, we can combine. So, see the logic operator and we can see the age of the class group in the class. So, in this particular case, for the class new and the domain age, and then we can also consider the class type on the domain of new domain representing the class. In this particular case, We can go further. We have relations, we will create rules. And in this particular case, you see the difference between these two. When we had the conjunction in this particular case of the two propositions, we have a little bit of a different combination between these two. In this case, we have if we have some domain and some fuzzy set, then there is in another domain another fuzzy set. So the same thing what we had before about the car and the price, we can translate, not translate, but change that into saying that if car, the age of the car is new, then its price is high. So in this particular case, we created something that if the input in this particular page is the age of the car, and someone tells us, okay, it's a new car. Of course, in this case, we do not specify the exact year, but eventually we will see the moment now. But that is translated into the time that the car is new, and then you see that the car is its price. And that is the condition, which is the age is new, and then there's a consequence if this price is high. So in other words, we already are able to build a fuzzy rule. And these fuzzy rules are the basic elements for any fuzzy-based system. So now we will take a look how we can put rules and eventually obtain some kind of through the inference, some kind of an output. So in this particular case, what we did, this is arithmetic mathematics. I will just show you that and then show the examples which will give you better understanding what is really happening. So we have a number of rules, something which we just talked about. For example, age of the car is new, then the price is high. We can have a number of these rules. And then we have some fun. For example, we say, okay, the car is 2 years old. So what we really do in this, and in this case, we try to infer some conclusion based on the definition which we have of the fuzzy set. And this is just how it's done, but I will just show you the example. So let's assume that we have a little bit more interesting rule, or few rules, saying that the engine is medium size, is medium in the case of the CC means the power. The size of the car is, or the engine is small, or the car is small, and the torque is small. Then if we have that rule, then someone who is expert says that then the price is small or low. The naming is not critical here, just the indication that if the engine is medium, the car is small, the torque is small, then the engine is 2 liters capacity, so the size here is in the engine, not of the car, 4 cylinders, and there's some specific torque. So then, based on that particular information, which someone told us, or expert says, that engine is medium, size of the engine is small, and torque is small, but the price is small. We have these facts, and we try to identify to what degree this is really the price is small. In other words, to what degree that particular rule fires. Because we say that if this part is satisfied, so the engine is medium, when the size is small and the torque is small, if all of these 3 conditions are satisfied, then we say that the rule fires. That means that the rule is valid. And that means that if the condition is satisfied, then the consequence means that the price is small. So how it is done in a fuzzy system. So first let me talk a little bit about the fact that we have 3 elements in our rule: engine, size, and torque. And here is representation of the fuzzy set, which means medium in the case of the size of the engine. In the case, the size in the sense of the capacity. Yes. So that means medium. We probably have something here regarding small and something here regarding large, but this is always shown here. The fuzzy set represents the concept of the medium. Then in the case of the size, we have also concept representing small.
It also could be medium, it could be also large, but in this case, we look at the number of cylinders and we say, okay, this is what we identified as small. Of course, here we'll have maybe one, probably engines, but it could be a small engine, yes. 1, 2, 3, 4, 5, and so on cylinders. That fuzzy set here, what you see this form, is representing a concept small engine. Here, on the other hand, is a small torque. The domain here is different. That would be in nanometers, but that in nanometers, and that will represent the concept small. We also have a concept regarding the price. And in this case, we also have the fuzzy set representing the price. So what really happens when now we have this three facts which we identified. The engine is 2000, size is 4 cylinders, and the torque is 400. We see that we look at this value of 2000 and we see, okay, this is the degree to which this value 2000 satisfies that fuzzy set medium. Let's say 0.2. But have you seen the things before? Okay, so let me continue with that. I hope that you have seen the things before. So we have this rule, which means that if the engine is medium, its size is small, and the torque is small, then price is small. So we have that particular information. Then the engine is 2000 cc's, there is a 4 cylinders engine, and there is the torque 440. We have a three membership functions of fuzzy sets, one representing the medium size of the engine, medium in case of the capacity, size small, torque small, and the price small. These three pieces of information which are entered or are facts, they are satisfying these membership functions, the fuzzy set, to a degree. So this one to a degree, let's say 0.3, this is, let's say, 0.5, and this one is 0.1. So in this particular case, we take the minimum across all of these three things, because this value of 440 satisfied that particular linguistic term, small torque, to a lowest degree. So we don't take the max, we don't take the medium, we take the minimum. And this minimum value of let's say 1, is translated and pushed towards the price. So right now, from that fuzzy set representing the small price, we have just a very small fraction of that fuzzy set activated. And then we use something which is called the diffusification. So in this case, it's the center of mass. We look where roughly it is middle and balancing this area which is in red, and that is associated with some specific value. So eventually, even if we have everything imprecise, through the very precise inputs, we go through the something which is called fusification, so going into the degrees. Then through the process of diffusification, we are obtaining again something which is more concrete. But the whole process of inference here is based on the fact that we use the linguistic labels representing the engine, the size, the torque, and the price in an imprecise manner. So there is also, that's kind of a smart, I will not cover that, but eventually that is involved because here we have just a one rule. In general, we can have more rules. So example will be here. Then we have rule, which we just talked about, the rule A. And we also have the rule, another one, which indicates that if this, in this particular case, I think I have another example which kind of fits exactly what we just talked about. So we talked about this rule, which is the engine is medium, the size is small, the torque is small, the price is small. Now we have another rule, which indicates that the engine is large, size is small, and torque is medium, then the price is medium. In this particular case, when the same values which we had before, 2000 cc, 4 cylinders, and 440 torque, when we run, or if we do look at the membership function associated with the second rule, the large engine, the small size, and the medium torque, we see that the minimum level of activation among these three fuzzy set is also here. It means also belong to torque, but now it is quite a larger degree or higher degree. So you see that in this particular case, we also have the fuzzy set representing the price. And in this case, what is really happening, we combine these two things together, as you can see here, and then this combined entity or body, we look at the diffusification. So we still again look at the center of the mass, and then the value which represents that center is the output, in this particular case, again, some kind of a price. So probably it will be, as you can kind of see, a little bit of a balance between something which looks like a small and something like a medium. So something between closer to the medium, because that mass coming from the medium is large. So probably we'll have something along the lines where the dot is. So that is the principle of building a fuzzy system. And in this case, you can have a multiple rules. You can have also the aspect of identifying different fuzzy sets. You will see that how it is done in the next presentation with the evolutionary computing, that you can adjust this rule depending on what data you have. So as a matter of fact, what you end up with, fuzzy control. In this case, we talked about this fuzzy knowledge base, which is this number of rules. We have some input, the fusification process, which kind of looks to what degree each of the membership function is satisfied. This whole thing is go through the inference engine, meaning combining all of the masses, if you remember from the previous slide. And then we have the diffusification interface, so looking at the center of the mass and getting a crisp world, and then maybe controlling or maybe getting some output. And then depending what this controller is about, we can create a new set of inputs, and that process continues in many cases. And that was where also one of the most significant contribution from the fuzzy logic is the fuzzy control. So with that, I would like to say that we've got learned a few things about the fuzziness, basic things, but I hope that it gives you enough interest and triggers some excitement, and then we will continue to study this concept, because we believe that that enables you to construct intelligent systems which are able to understand better how we human communicate and how we talk, and how we, even being imprecise, can do different things nicely. So I hope that gives you a little bit of an introduction with some glimpses what the fuzziness, fuzzy rules, and fuzzy inference being the fuzzy system is. So, thank you very much.
Thank you, Professor Murray, for the talk just now. Ladies and gentlemen, our next speaker is currently a professor in the Department of Computer Science and Information Engineering at the National University of Thailand, Taiwan. He obtained his PhD degree from the Department of Computer Science and Information Engineering at National Cheng University in 1998. He was honored as an outstanding contributor to Information Education and Taiwan Academic Network for the 2009 academic year by the Ministry of Education. In 2023, he received the Excellent Award at the NSTC Industry and Academic Project. He was honored with the 2022 IEEE ERB Meritorious Achievement Award in Green Education. Please welcome Professor Cheng Xing Li with the topic Content Attention Ontology CAO Robot with Computational Intelligence for Human and Machine Co-Learning.
Okay, thank you. Hello, everyone. It's my great pleasure to share our experience about the CAO robot. I think the robot is important for now and for the future, especially for the large language model, just similar the ChatGPT. So later we will invite all of you to do some experience about the Taiwanese ChatGPT. Maybe you can speak in English, in Chinese, or in Taiwanese language, Hokkien. Okay, and any language, then if you speak human language, then we can generate some image for you. Then for in the future, if we have quantum computer, then we hope maybe 5 years later or 10 years later, the quantum computing and quantum AI will change our real life. So my talk is about the CAO robot with computational intelligence for human and machine co-learning. I think now is time for us to learn from machine, and machine can learn from human. So in Chinese is 观察技, observe ourselves and human-centered intelligence, deep learning, human knowledge, and design our goal and achieve our taste. So I'm Zhang Xinli from National University of Tainan. Today, later, the Mei Hui and my student Zhi will share, and we invite all of you to do some experience. So thank you for IEEE R10, SPNIC, and EAC activity in my share next time. Okay, so today we will three parts. Part one, I will show some video for you for the human and machine co-learning. The first is student and robot co-learning model. I think now is very important for the young student, especially for the high school student or undergraduate student. And next, we propose the content attention ontology with Professor Marek in Canada. So I think the ontology is a knowledge model, especially for the human knowledge model. So we propose the CAO robot with Hasushua-based human-machine interaction. So first, I will show one video for you. We co-work with Professor Kubota in Japan. So please, thank you. Speech translation.
Good afternoon. Thank you very much for your participation. We design the system with CAO based robot for human machine interaction. So this collaboration is done with Professor Chan Xing from National University of Taiwan. So today, we conduct some experiments on human machine interaction. So we start the demonstration of text to image AI system.
In Taiwanese language, then generate the image, and with the Japanese robot. Japanese ramen is delicious. 日本拉面好吃 in Taiwanese. In Taiwanese. Then Japanese sashimi is delicious. So in Japan, in Tokyo. So we invite all of you to join us in June in Yokohama for the similar event in Japan this June, the big conference, IEEE big conference, and next, please. Then I prepare some video for you, okay?
Hello everyone, we are the team from
So we messed up.
Taiwan. Today we will introduce generative AI to assist with Taiwanese language learning and teaching. First grade and second grade elementary school students experience generative AI through interaction with the new TNQCIMJI robot or by using other language tools. Next, we will use the large language model, which is wider.
TED is supported by Taiwan government. Speak in Taiwanese. Then speak in Taiwanese. And this is in the elementary school student in Taiwan. And you can see the young student.
Design and interact with NUTN robot for interactive Taiwanese learning and data collection. Here we use the generative AI text-speech to event platform, where we can input Chinese or English text on the top, and we can speak.
So later, all of you can try to use the system. Use this system.
The learning platform will generate information
in Chinese. So later you will generate this one. Okay, we do some tests in Japan, in Taiwan, then in Malaysia, and April we will in Hong Kong, and in June we will back to Japan again. So next, I will show another video for you. GAI. Malaysia is here.
The figure marks the transition from the completion to programming paradigms. The period between 2009 and 2016 is the human and computer competition.
2009 in Korea. 15 years ago, we start this research. And this is in Spain, 2010.
And from 2017 to 2024, now the human and machine co-learning. This is for the net training data of this.
So later, all of you will do the what?
Using ice, hot water, and hand plugging to change the values.
Competition presentation.
We control the temperature, humidity, light, and the distance between the place and the light. And this is our research method to use ESL and other systems in this project. This figure is the QCM module with GAI in 2024. First, it introduced CI integration, application, and learning alongside HI. Next, it is about HI perception, cognition, and implosion, which met with an NFL and ECOCI. And we can see this webpage show the event in Hong Kong. Code of a
Next month in Hong Kong.
And we can,
City University of Hong Kong.
Webpage, we can see the teaching videos, samples, and IEEE R10 information and a poster. And we can see this webpage shows the event in Malaysia.
Today. So later you will go to this website.
The webpage also has the teaching video, the samples, and IEEE R10 information and the posters. We can see this page shows the event in Japan held on February 20. The website also has the teaching videos, samples, but here are the activity videos. After clicking on it, you can see the gallery videos in Japan. Thank you, everyone.
Okay, thank you. So later all of you can use the learning platform. And next, please.
Hello everyone, we are the International University of Taiwan. Today we will introduce this speaker. This speaker
So later you can use this system.
AI interactive platform that is
So later you can use this platform to speak English or Chinese or Taiwanese.
interaction of multi-model data types. It is designed to facilitate human-machine interaction by using AI technologies to generate image, text, or voice output from various inputs, enabling co-learning of language between learners and machines. During the input phase, learning can choose from three options. Number one, text tag, allowing for English or Chinese text input. Number two, voice tag, enabling English, Chinese, or Taiwanese voice input. And number three, image tag. Upon receiving text data for the purpose, the adult image generation AI model, offering the text to image and voice to image mode, can create virtual representations and generate an image of the relation starting directly, along with the image sentence. Moreover, the data in practice model is used to transform between English and Taiwanese voice. In addition to these text-to-image capabilities, the platform can also generate natural or spoken outputs in different languages for the content summarization.
So later you can use the image to generate the English voice.
The kitchen has a refrigerator, oven, and sink with 2 bottles and a knife at the top. 这位请勿请勿拿起的山寨来。
Taiwanese voice.
Finally, the data of
this English application are stored in the repository of art, mixing and validating and the QCI learning model. Thank you, everyone.
Okay, so later you can use the correct data to generate the quantum computational intelligence model for the software. And in the future, if we have quantum computer, we can execute on the quantum computer. So next, I think we will have 2 videos with some students with Professor Hafiz and in here. So next.
Use the PCI and learning tools to
So later you will use this one.
When a machine receives data, it responds with actions such as displaying information on displays, verbalizing the information, and triggering hardware actions. Learning tools receives data from a PCI and a learning platform. Learning tools only publishes data manually to the PCI and a learning platform.
So this video is important for you. Later you will correct the program.
Learning tools publishes data automatically to the PCI and a learning platform.
The machine can also automatically collect data to publish to the learning platform for inference and the learning simply from result to respond with actions. Attributed to one connection, speech English or Taiwanese to generate images. 这些案例我哋讲嘅。Students in Malaysia use learning platform connected to the learning tools in Malaysia.
So we do the test between Taiwan and Malaysia. The student in Taiwan and student in Malaysia.
Students in Malaysia use learning platform connected to the learning tools in Taiwan. Students in Malaysia use learning platform connected to the learning tools in Taiwan.
Okay, thank you. Then next, the final video. Okay. Some feedback from the student.
Expressional learning.
One thing I can say is just never stop learning. You never know. My father used to tell me, everything you learn, you will need to make. Nothing you learn from grade school, you will need to make. So just continue learning, and you always try to be a visibility of yourself, to use something to other people who you care about.
That's a good experience. I think that you and be uncomfortable.
It's quite challenging because you really feel because I like the and happy or experience.
So that's like a lesson in learning. Engaging people, exchange of technical knowledge with people from different countries bring me great satisfaction and joy.
Thank you very much for the opportunity. I live and innovate in Taiwan to represent everyone is capable and doing the platform and the student. Thank you very much once again. Thank you. See you. Bye.
Closing remarks. Thank you for joining this free training activity, and we hope to see you again in Malaysia. Roll photo.
Okay, this is the Monday evening from 10 to 10 and 9 or 10. 9 to 11. Between Taiwan and Malaysia, the student collect together. And later they will teach you, the high school student here and next, okay? So I think the CLO robot and the CLO-based content attention ontology is important for the student learning and even for the robot learning. So we use the Meta AI, the Facebook, the Meta AI test, the open source and sentence bird, and for the ChatGPT all together. So later you can try everything. So next time. So as Professor Margaret Reformer introduced the 5 logical, so the CI computational intelligence with human intelligence is important for the future young student learning. So the CI computational intelligence is one of the core technology of AI. It composed of 5 logical, FLO, neural network, and evolution computation. So later the Marcus from Australia will introduce the evolution computation. And after Professor Marcus' introduction, then you can use the PSO to train your model to do the model inference. So we use the finite markup language FML. FML finite markup language is proposed by European research team in 2003 and published in IEEE International Journal in 2005. And now is the IEEE 1855 standard in 2016. In the future, we hope some company and some university in Malaysia can co-work with us to promote the quantum language for the software and hardware together. So next. So we combine the human in the loop to combine the Western AI and HI and Eastern AI and HI together. So as you know, the ontology is the language model, and Turing is the father of the AI, and the Xuan Zhang, he proposed the important concept for the human intelligence. So next. So there are 260 words for the Hard Sutra. So next. So we use the HAI, human-centered AI, for reinforcement learning, human-machine co-learning with the HAI for RLO. So we use the human-centered AI. So agent can help us to do many things, and the agent can observe the teacher and student together in the location with time domain and space domain. Because now in March is 30, and in Malaysia, and we hope we have an interactive environment with the ontology, especially for the CAO content attention ontology. So next. So we hope the teacher and the student can deep learning together, especially the human and robot also can deep learning together based on the human and intelligence. For example, the teacher can design the objective function and loss function, and the student will achieve the goal and the task. So next. So we co-work with Professor Margaret Foreman last year, and we propose the content attention ontology the next. So this is for the English version. So next. So you can see here is the human intelligence, and here is the artificial intelligence and the machine intelligence and the fuzzy ontology here. So now later we will use some learning tool. So we also have one video for you. Last year in Japan.
I am going to Tokyo, Japan for research in February this year.
To be starting international research projects and collaboration in the research lab.
So in Taiwanese language. So later you can try.
因两个人身体中大的时阵，讲到家己啦。
I am going to Tokyo, Japan for research in February this year.
笑声我要来去东京啦，今年2月研究啦。
We will be discussing international research projects and collaboration in research lab. Take care of them.
So now she can speak Taiwanese language.
Going to go to Japan for research in February this year.
我要去日本做研究啦，今年2月啦。
In February this year.
我要来去日本做今年2月研究啦。
I will be visiting Filipino University with my wife and 2 students to meet the curriculum of mine.
我甲我的探究，还有2个学生作为参观一所著名的大学，去交我一个好朋友啊。
So today we will also prepare some sentence for you, so you can see, including the junior high school, the girl, and some undergraduate students, some master student, and some PhD student, and some professor. They speak the same sentence, then can generate the Taiwanese language and the Chinese language. So we design the same system for all you later. So next time. So our ground truth we provide by the IEEE CIS computational intelligence society for the ground truth. So you can see the ground truth is here. For the elementary school students, they can learn some knowledge. So the knowledge quality is not so many. So this is for the high school, junior high school student and senior high school student and undergraduate student. And if you are PhD student, you can learn all of the computational intelligence. So the meta intelligence, including the time and space with the mapping function. So the knowledge quantity is quite different. So if you are high school student, maybe you learn this one is okay. If you are undergraduate student, maybe you should learn more knowledge for you. But now, because we have the large language model, for example, the ChatGPT or different kind of large language model, they can help us to co-learn together. So next. So this is the relationship between the component for the human intelligence and artificial intelligence. This is for the Eastern human intelligence, and this is for the Western human intelligence with ontology. And this is artificial intelligence with the computational intelligence, Turing and Day. So this is for the elementary school student, junior high school, senior high school, and the university student. They can do some real-world application. So later, we invite all of you to do some real-world application for the CI application, for the learning concept. So finally, we will construct the ontology with the robot and the learning tool together. So next. So I think last year in Taiwan, we already have similar event between Taiwan and Japan. So please show this video. Thank you.
Sometimes I need to paraphrase.
好。
Observe and attend. The teacher observes the abilities of the learners, prepares the corresponding CI teaching content, and goes to the teaching site. Step 2 and 3. Study and research. In the teaching field, the teacher and the learners experience CI concept-based learning together and conduct in-depth research on the corresponding CI content. Step 4. Utilize and follow. After CI learning, the learners can use and follow them for CI experience-based learning. Step 5. Understand and know. After CI experience-based learning, learners understand and know the principles of CI and can carry out CI practice-based and operation-based learning. Step 6. Explain and speak. Learners can explain and describe the CI learning content to other learners for CI expression-based learning.
And from this event, I also learned very great tools such as Google ChatGPT and Kubernetes.
It was helpful for me as I plan to deal with AI in my school self.
Also, my mission has been teachers to focus on the teaching and engaging with students.
The first answer from Professor Pupanda, I learned the basic idea of the artificial intelligence.
The background of basic concepts of neural networks are evolutionary computation.
And I have a better understanding through the teachable machine.
And nice to know what kind of education and how students are learning overseas.
I have had some experience to learn artificial intelligence.
It was nice to meet the people from different countries.
I will teach the machine to recognize mobile phone. Wi-Fi has and charging cables.
But the core Wi-Fi just lagged my back, leading to serious delay while I tried to control the robotic field.
The teamwork was excellent and the collaboration was very enjoyable.
It was a great learning experience.
I learned a lot about artificial intelligence and
All high school students are similar, the same age, the same age.
New generation, I learned about
artificial intelligence. Today I played crucial and neutron. I'm very enjoyable.
I think this event is a good opportunity to learn about AI-related knowledge.
And I hope everyone can enjoy today's lesson.
I'm excited about teaching students for a senior high school.
So the high school is in southern Taiwan, so in senior high school.
Thank you very much for your joining and watching.
Okay, so next. So I think if you can understand Chinese, one teacher with 3 students, Sun Wukong, Zhu Bajie, and Shao Jin. So I think this is our important concept for the human and robot co-learning. So the video is one. For the young student learning, we prepare some video for you. So this is for the file system, just as Professor Marek introduced. So later you use the PSO, the algorithm. Okay, so we invite all of you to join our activity for the computational intelligence for the young student learning. Okay, so next. Okay. So we also have 3 videos, but we play first one and second one. First one, about 1 minute. You can use this one to control this one. This is for the elementary school student learning. Okay, thank you. So next. Okay, thank you. So the second, for the high school student, undergraduate student, we do some tests for you.
Step 1. Students write 2 or 3 simple Chinese sentences. Step 2. Using AI tools like ChatGPT to translate into English. Step 3. Students use abilities to describe instruction and use AI robots to translate into English words and pronunciation. Step 4. Students use English to describe instruction and use AI robots to translate into Chinese words and pronunciation. Step 5. Machines and humans separately evaluate the performance and accuracy of the AI agent's human language semantic translation.
So later you can use the computer, your notebook, or your cell phone to test. In the future, if you have robot, you also can speak to the robot to commute directly. Then the notebook, the cell phone, the robot can speak to you in Taiwanese or in English.
谢谢。Thank you very much.
Okay, because the time. So next. No, this one no, because the time constraint. Okay. Next page. Okay, so I think maybe the final two video, we show this video. Okay. Also in Tokyo.
It's our pleasure to have a meeting with top video members. Stand by for digital CI of the university.
就不播，对，好，那我们这个就可以讲。好，
所以如果要分享电脑要拿到这边投影嘛？
等一下。
We hope to increase students' interest in mathematics.
So last year in Japan, we also co-work with some professors in Japan. So this is the video you see. The Professor Lee from Hong Kong. Okay, this is the event in Japan last year. Okay, next page. So we co-work with Professor Marek Reformer about this research and next page. So next, I will quickly introduce the CAO-based robot, and later all of you can try the CAO-based robot. So next. So this is the transformer-based. So if you are interested, maybe in the future we can introduce this in more detail. So next. So we use the speech-to-speech translation S to ST for the ASR automatic speech recognition by English, by Chinese, or by Taiwanese. Then machine translation MT, finally text to speech TTS. So later all of you can try. So this is directly S to ST approach for English language to Taiwanese language directly. So next. So we also do TV report in Taiwan, but all the report is in Taiwanese language. So the first one, please, thank you. So the first is in the elementary school student learning. So this is Taiwan TV and the pronunciation in Taiwanese language. So I am student speak to the robot directly. So in the future, we hope here we have this robot to connect with the student. So students can learn English and Taiwanese language together. So the teacher. So you can design your AI to this robot, the software with the hardware together. So Japanese professor also go to Taiwan to do the test.
How long do you have? Is it going to be the answer? Or you have few more minutes?
One. Okay, because of the time constraint, so we will skip this one, no, the next. So last year in Chicago, in American, we also have 2 events. So first one, we invite some professor from Germany, from American to do the test. Germany.
This is not my bicycle.
In Taiwanese. Washing pants. So Thomas. Joanna in American. She speaks Taiwanese language. Then translate to Taiwanese. Last year in Chicago, and this year we are in Japan. And next video in Korea last year, okay? Next video. Yeah, this one. In Korea, South Korea. Oh, some professor. It's delicious. The same sentence. 金喝价. It's delicious. Jenny Mendel. How are you? So later you can try if you. Amir. He also will go to Japan this year together. Okay, because of the time constraint, so next maybe next page. Then later, I hope you can use the quantum CI with the GAI Gen AI, generative AI, to generate the image based on the quantum computational intelligence with GI image. For the English Chinese text to GI image, or for the Taiwanese voice to GI image. And we use the CAO robot for the GI image to test by the software and the hardware together. So later you will use the hardware design and use the software to the hardware all together. So next. So we will present this paper in Japan this year for the quantum computational intelligence with the generative AI image for human-machine interaction. We co-work with some professor in Japan, in Italy, German Campera, or in different countries, or in Canada. So next. So later, I hope all of you this afternoon you can finish and generate this the quantum circuit for the real world application. You can speak in English, in Chinese, or in Taiwanese language, then generate this image. And based on the fuzzy set, just Professor Margaret Reformer introduced the fuzzy set. And based on the PSO later, Marcus will introduce the evolutionary computation, the PSO particle swarm optimization, and next. So next. So finally, thank you, and I hope all of you can deep learning the human knowledge and design the goal and achieve the task based on the human-centered AI, artificial intelligence, and human intelligence. And I would like to also to thank you the Taiwanese team, the Margaret in Canada, and Giovanni Acampora from Italy, and IEEE R10, and IEEE Computational Intelligence Society. Okay, thank you very much. Okay.
The first for his school and for Best Paper Awards as well as a Humis Gold Award. So far, he has written over 150 articles with more than 200 different co-authors. Please welcome our last speaker, Associate Professor Marcus Wagner, with his topic Introduction to Evolutionary Computation.
Fantastic, thank you. I shall try this. This is always a bit scary whether this works or not. One moment, please. Escape. I have trouble finding it. Well, give me one moment, please. All right. Good afternoon, everybody. Oops, sorry, already too far. Please apologize, I am briefly jumping around. May I ask, can anyone give me a thumbs up for whether they can see my screen or not? Okay as well? Okay, fantastic. Thank you. Good morning, everybody. I'm very delighted to be here today. It's a great pleasure, and I will be connecting to a few things that Changxing has said in terms of outlining to you one of the core technologies in artificial intelligence. My name is Marcus. I will be around afterwards for a couple of questions in case you would like to ask any questions. Also, I will, so my next couple of minutes are going to be very high level. Normally, I spend an entire semester going into all the tiny details here of evolutionary computation and swarm intelligence. For the next 20 or so minutes, I will keep it relatively high level. All right, let's go. So we are going to explore nature's algorithms. All right, what do I mean with nature's algorithms? So there are, nature has been able to solve many problems over the years, decades, centuries, millions of years, and we as computer scientists explore these mechanisms. We get inspired by nature. We see how nature manages to evolve trees and essentially create trees that live better and better, or flowers, or groups of animals. And for us, these paradigms, they can be inspiration to new problem-solving techniques that we can use in IT, in computer science. And I will go largely through two slightly different areas here. One is evolutionary computation, and the other one is swarm intelligence. Throughout the next 20 minutes or so, I will be jumping around a little bit. Sometimes I'll be more on the evolutionary computation side, sometimes more on the swarm intelligence side. And in all cases, we'd like to harness the power of algorithms, the power of problem-solving recipes as inspired by nature to solve complex problems. Let us start with evolutionary computation and maybe just a tiny little bit of history. So about 200 years ago, Charles Darwin on the HMS Beagle, so that's this ship here, sailed around the world and collected lots of birds and specimens and made notes about what he observed in nature, plants, and also in terms of animals that he encountered. Now, at the Galapagos Islands, he collected several specimens of birds, and once he returned to London, he noticed, or his colleagues actually noticed, that even though all these birds, they all are finches, so finches is a particular type of bird, they all were quite different. And it turned out that on each island of the Galapagos Islands, or largely on the different islands of the Galapagos Islands, different finches seem to have evolved in different ways, adapted to the problems at hand, to the conditions, to the seeds that were available. So they're all finches, but as you can see, for example, with very different beaks, probably to eat seeds of different kinds. This can be seen as a breakthrough discovery because it shows that different solutions exist for different niches, and they're all kind of equally good or good in their own right. Now, for us in IT, we can try to leverage this, and we can simulate the idea of evolution. And I will go through this particular picture here in a few minutes, a little longer. We can harness this general concept of having a population that generates new kids. So a population undergoes reproduction, and there are some survivals of sorts, and then we go round and round in the circle of, well, mating, reproducing, creating better and better solutions for the current situation at hand. So this is what we'll be looking at for in the next few minutes. In particular, I would like to briefly mention that in evolutionary computation, this is actually a bit of an umbrella term. In this paradigm here, in this idea of going round and round, not in circles, but in generations, there's an entire family of different approaches. We've got, for example, evolutionary algorithms, genetic programming, evolutionary strategies, and so on. I only have time here to briefly talk very, very briefly about genetic algorithms and genetic programming, but there is much, much more out there. Let's come to swarm intelligence. Now, behavior, collective behavior of centralized, self-organized systems in nature. Yeah, no, and with decentralized, I mean, there's not a single leader bird necessarily here in this swarm that tells it, let's do this now or that now. These algorithms, they mimic the behavior of social insects and particles to solve complex problems. For example, when birds flock, they do, also, for example, starlings and geese, they form large flocks that move together in particular patterns, in coordinated patterns. Each bird in the flock follows simple rules based on the movement of its neighbors, resulting in complex and synchronized group behavior. Flocking helps birds navigate, evade predators, and as you can see here next, birds flock together and it helps them to find food here. Fish schools such as sardines and herring also form, or they move in unison, creating patterns in the water. Fish schools help individuals who can find food, navigate, and evade predators. Each fish adjusts movements based on the behavior of its resulting in coordinated group behavior. In ant colonies, ants exhibit sophisticated collective behavior when foraging for food. They communicate with each other either through touch or through pheromones, and this enables them to solve complex problems without a particular leader always delegating, like a general of sorts or grandma of sorts, telling ants, do this now, do that now. And very much like ants, termites also do not appear to have, at least to the best of our knowledge, any centralized control, but they create very elaborate mounds, these hills that serve as their nests. The construction process involves thousands of termites working together without any central coordination, and through simple interactions and local rules, termites build these complex structures with ventilation shafts and resting areas and so on. Very impressive. All these examples together, they demonstrate that how simple interactions between individuals can give rise to complex, adaptive, and intelligent group behavior. I will see how we can actually implement this, because we are saying in a few minutes, because things like this we can easily observe, but how do we tell the computer that we want to use this to solve a problem? Well, just for a moment, let us briefly jump back to genetic algorithms. Why do we actually need to consider something like a genetic algorithm? Well, sometimes we are simply facing a problem, or we want a computer to solve a problem. So, for example, let's keep it very, very simple, don't worry, it's not going to become very mathematical here. Your task is to find the best, highest solution here. So this is your particular part. So you have a function f of x being simply this curve here. You have seen it many times, for example, minus x squared or so. It's not really minus x squared shape, but you get the idea, right? You have some tiny problem, and if you have a tiny problem, you can potentially just try out all the different combinations, all the different approaches to solving this problem. Now, if you have, well, in the reality, you don't just have tiny problems, you have really large problems, and sometimes parts of the space you can actually not implement, maybe because you're violating the budget, or you just cannot have two agents or two particles or two things happening at the same time, because they would crash into each other. There can be lots and lots of constraints, and sometimes these constraints even render what may be a really good solution just infeasible. So now when we have here such a space, if you have just a single variable, we can probably still enumerate lots and lots of different solutions. But imagine we go into 2 dimensions, x and y, 2 variables, 3 variables, 100 variables, 1,000 variables. You can probably imagine that navigating this space becomes incredibly difficult. What can at times make things even more difficult, so one step too many, is we don't always have the full mathematical understanding of the problem that we are trying to solve. Sure, we have a definition of sorts and we can press a button, but the simulator or a simulator might give us only the result. This situation, or in this situation, we often have to rely on something that is called black box optimization. So a problem, we may have a little bit of an idea, but essentially we put a solution in, like x equals 5, and we get a quality out like 16 or so. And that's all. Then all we can do is maybe generate a solution here, generate here, generate here, generate here. despite all these difficulties, we can have very amazing, or simple but also amazing, successful approaches that can allow us to find great solutions, also when the landscape changes. So we may, as I mentioned, all these little points here, these are candidate solutions. To predictions, changes, and so on. So this is, keep in mind, this is a very simple situation. In such it might simply be too limited. It might give us the solution once, but afterwards it might not be able to dynamically adapt to a changing landscape. So this is one of the great advantages of a population-based approach, evolutionary computation approach, or swarm intelligence approach, that it tends to work quite well here on dynamic problems as well. All right, so now very briefly, what can a genetic algorithm look like? Again, normally I would spend about 2 hours just on this very genetic algorithm. Let's keep it very high level for now. In the computer, when we employ genetic algorithms, we typically do not use DNA, but we use lists of numbers. For example, we can encode one solution in one particular person as 103 ... and another person with maybe a bigger head and smaller legs and arms might be 326 ... and so on. All right, so we just use a different alphabet of sorts to encode our solutions. At the beginning of our genetic algorithm, we initialize, we start with a number of different solutions or candidate solutions to our problem. So please keep this in mind. A solution here in my language is not only the very best, but it's anything that you can implement. So let's say candidate, that's why I say solution candidate or candidate solution. I will probably regularly forget to say candidate, but I always mean that it's a solution, it's something that you can build. And some of these solutions, they tend to be better. For example, 9, let's assume we're maximizing a 9 better than a 2. Now, once we have created this initial set of solutions, we press a button and say, all right, now we select from this population a couple of solutions that we think are maybe good, and they should be parents. These should then reproduce and produce children. Okay, sorry for cutting this off here. So, for example, if I have a parent like 103, not all the blue colors, and 326, and red, I can maybe just exchange some information, like exchange information on the length or the thickness of the legs, or the thickness of the head, or size of the head, and so on. So just from these two parents, I can already start to create lots and lots of different solutions. And this gives me then, so you can kind of see this here, 2 parents together break 1 child. So that's a good starting point. We could already leave it there. But we can go one step further. We may or may not have heard of mutations in the real world. Sometimes external factors like UV sun rays or so, they might result in a mutation, in a change, an involuntary change of your genome. And what mutation does is it simply changes some of the numbers. It might just change a single number, let's say from a 0 to a 1, or it might change 2 numbers here from 1 to 7, 6 to 4. But believe me, there's about 1 million different ways how you can do this. For now, let's just keep in mind that mutation just takes one child, for example, and does a change to it. And in reproduction, in recombination, you have 2 parents producing 1 child. Alright, so once you have created the reproduction, mutation in your population, you check how good they are, and then you go round and round and round. And ideally, because you do always select the best ones, your quality gets better and better and better. At least that's the idea. Quite in contrast to this, in uncolony optimization, there is no global control. We do not have this big loop that goes around and around and that selects from the very best, from the population, the best solutions. In uncolony optimization, there is no, as I said, no global control, but the ants, let's call them just ants for now, they exchange information. This can be in the real world, via direct communication where other ants are recruited and essentially they tell each other, hey, help me with this, or let's get this piece of a leaf over to our burrow and so on. The ants also communicate, or some at least indirectly, via pheromones. So these are chemicals that, as an ant moves around, it leaves behind some chemicals. And ants also consider these chemicals when they have to make a decision. For example, they could go here to the right, where there seems to be a relatively small amount of pheromone, and here to the left, where there seems to be a lot more of this pheromone. As a consequence, you have sometimes these streets of, at least that's how I would translate it, or the highways, ant highways emerging. You see, there's no ant here, there's no ant here, but between these 2 points, the ants seem to have found a really efficient way of getting from A to B. Good. How can we potentially implement this? Well, let's do a simple thought experiment just for a moment, just to see how can this actually work. We will not go into the implementation part here. Let's assume ants are here in a particular spot here on the left, and we are going to send the 6 ants out. Just by random choice, 3 are taking the upper path, 3 are taking the lower path. They all find to the food source. And some ants pick up some food, and then they are already ready to go back, and while the others are still traveling. Okay, or nothing. Already here. Because the others are already traveling, for the first ones that are already already on the way back, they will not have seen that this is already a possibility. So they don't actually have a choice. They will follow the stronger path. And because they're following the stronger path, they end up depositing more pheromones again along this. So they're kind of reinforcing the shorter path. They can reinforce it because these chemicals here, they reduce over time, they evaporate, they break up. Otherwise, we would have a big problem. There would just be more and more chemicals that break up. So the reinforcement here of a good solution, of a direct connection between the nest and the food happens because these pheromones that dissipate over time. And the ants, again, like here, when they have the choice between a stronger path and a weaker path, probabilistically, there's a higher chance for them to take the stronger path. We can use this in computers, for example, to optimize our tools for delivery trucks. I will not jump over there because it's otherwise going to cost about 5 minutes time. Let's see if we happen to have time. Maybe I'll briefly jump into this later. Good. So that's something here on ant colony optimization. Let's just jump very briefly into another paradigm that I haven't mentioned here. So in the swarm intelligence space, you've got concepts like ant colony optimization, particle swarm optimization, and many others. In particle optimization, just like with the ants, you also have no central control, but you've got these and we know that at some point it has seen its personal best, PI, personal best. And at each point, because it's moving around, it also has a velocity. We bring them together, well, we let them exchange a little bit of information. The previous best would be. We also share with the others, or the entire swarm exchange information, and they know, okay, where's globally in the entire swarm the best solution, and it might just be over here. So we are currently here, we know that our previous best is here, the global best that the entire swarm has seen, this is the only piece of information that they are going to exchange now, the global best of the entire swarm has been seen here. So let's do the following. I've got my previous vector pointing in one direction for the velocity. I take some part of, well, essentially trying to pull me again into the direction of the personal best. then some fraction of that point pushing me into direction, pulling me into the direction of the global best, and as a consequence, this is what my velocity vector might look like. So I'm currently here. These are the other two good solutions, my own, the other global one, and I might be saying, okay, let's move this direction. In this little video here, don't worry if you can't really see it, visualized are some food sources where, so these are targets, these are little yellow discs, sorry, it's maybe a bit hectic here, and you've got swarms of different colors and different properties moving around. So this blue swarm that just disappeared, that seems to be eating up the yellow disc here, and this other one here tries to catch the food source here on the other side, the left side. And what's happening here is that, again, they all know how close they are to the food source, they all know how close the closest one was, and this then helps the particles to get closer and closer. And find better solutions, get closer to food source, and then consume the food source, of course. Let's go further. Good. But we don't have to stop at just lists of numbers. So let me again jump back to this evolutionary computation. It's always going a bit back and forth here. We don't have to limit ourselves to just lists of numbers like 3 to 0 and so on to encode how big a head is and how long the legs are and so on. We can use entire formulas and change these over time. For example, in the context of data science. So we might want to express, or for a particular data set, we might not know what the relationship is between various pieces of data or in large data sets. So we might be looking for trees, for structures like these that can express this in a human readable form, not just use a neural network, which is not really understandable, but maybe we are looking for a somewhat easy or human readable version. So we can evolve this, and we'll see in a moment how we can potentially get there. But also we can evolve computer programs. And that's what I focused in some of my research on. So here we have an entire, on the left side, a computer program setting I to equals 1, and then a super simple just an increment here in the while loop. You may have seen something like this already. As represented in a graph structure, we can, or it may look like this, where we have I equals 1, and then a semicolon, and then a while loop, where we have a condition, and then the body of the loop. Once you see this, it's no magic. So no black magic. But now you wonder, okay, Marcus, how can I do the recombination or the crossover of information? How can I do the mutation? Well, let's have a quick look at one example here. So what is happening here in this particular solution is, so we'll wait for the starting point again. So this is the starting point, and the mutation now just deletes part of our tree, and it recrafts, it regenerates parts. So this is a simple mutation. You can define it. Okay, you can do whatever you want. You can change an X to a Y, a 3.2 to an 18.0, and so on. There are many, many ways with how you can modify these formulas and then check, are they good, better, or worse, for example, using mean squared error. Crossover is maybe a little bit more involved. As you can see here, you can recombine information. For example, when you have one parent on the left, one on the right. Let's wait for the beginning of the here again. So we discard here again some part of the solution and recombine. We will take some part over from the other parent. Now in this case here, it might or might not make very much sense, but in practice or academics, they use these approaches very much. All right, let's come to some examples. I will focus a little bit on my success stories because I have a couple, but believe me, there are thousands and thousands of other success stories out there. Companies are making a lot of money with these approaches. For example, I've had, one of my students went to Boston Consulting, one of my students went to Intel, one of my students went to Domino's Pizza, so he's optimizing the routing there of the pizza drivers. What have I done with evolutionary computations in particular? Well, for example, I've had a collaboration with the Australian Institute of Sports trying to make their cyclists in track cycling faster. I've had a very different problem where in ore stockpiling, where you have these giant stockpiles, these mountains, and you optimize essentially how you deposit ore and reclaim it. If you have a Chrome browser, which you may or may not be using at the moment, there's actually a tiny component in there that was generated by me and my team that's responsible for encrypting and decrypting your code. And that's Google funded. I've had a project with Carnegie Clean Energy on their wave energy converter technology, exploring or really pushing their technology to the maximum. And I've had a project with Facebook, so it's also funded by Facebook, on bug fixing or finding bugs, but not bug fixing, but bug finding in the social network. So there's a million other, or 1,000 other great success stories out there. For example, one that some of my colleagues like to mention is a few years ago, an evolved and optimized antenna on a satellite was actually sent into space. And this antenna was much, much better than anything that humans would produce with all their domain knowledge. So this unbiasedness is a big advantage. Advantages and disadvantages, I will keep this extremely short, of evolutionary computation and swarm intelligence. One big advantage is they can sometimes find optimal or nearly optimal, so really good solutions for complex real-world problems. But the disadvantage is that there's no guarantee that they find actually optimal solutions. They will find some solutions, but typically you simply have no idea how far away you are from the optimal. Just something to keep in mind. All these different approaches, they can be very easy to set up, and they can be self-adaptive. As you've seen, they can move around as the landscape changes, but they can actually, if you get the maximum out of your approach, it takes quite some experience to set them up correctly. They're always produced, they set some solutions, but if you set some parameters wrong, the performance can be not so great. And one last thing I want to do is we have multiple objectives. For example, you want to design a car and you want to trade off speed and comfort. That's a great technology to work with, evolutionary computation. But if you have many constraints, for example, you don't want to spend more than $10,000 on a car or so, evolutionary computation sometimes is a bit tricky, not as good as mathematical approaches. Just two more slides. Where are we heading with the entire field? It's already heading in many different directions, better applications, but it's also trying to making use of all the machine learning that's happening. So, for example, so the machine learning is used to make evolutionary computation better and swarm intelligence better, but you can also use these methods to actually make machine learning better. For example, what should the structure be of a neural network? You can use evolution to optimize the structure, and then you can save resources. There's also a lot of work happening on hybridizing, on combining all these methods that I've ever so briefly outlined with proper mathematical methods to yield a massive performance boost. And one last point I want to super briefly mention is some colleagues of mine, I'm not affiliated here, but just some colleagues of mine in the UK, they have created a lab of sorts where robots can evolve autonomously. So you've got a robot printer, a fabricator, you've got a kindergarten for little robots, they can go out and solve problems, or what it's called an arena, they're not battling each other, but they can do stuff here. And at some point they die and they get recycled, and then the components can go back into the fabricator pyramid here. I find this a very revolutionary idea. Sky's the limit, really. All right, after this quick jumping around through a couple of topics, what do I want to leave you with? To me, evolutionary computation and swarm intelligence is really a superpower. It can leverage all the machine learning advantages that are there now, and it leverages the insights from data science to then provide decision support. That's what humans typically are after. They want to know, what shall I do in this situation? What shall I do in that situation? And then optimization can be immensely powerful. If that interests you, study something in the greater space of computer science, algorithms, engineering, or biology. As I've briefly alluded to, there are many careers in different areas possible, such as consulting, academia, large companies need optimizers, small companies need optimizers, and so on. And as one of the people said in the video, don't stop learning, always keep learning. I'll wrap up here with a comment by Charles Darwin, who said, the strongest of the species that survives, nor the most intelligent one, the one most responsive to change, so the one that can adapt, the one that can improve. And with that, I'm concluding my brief rush through evolution and computational and swarm intelligence. If you have any questions, feel free to ask me now or during the lunch break, or contact me via email, please. Thank you.
Thank you, Associate Professor Marcus Wagner, for the talk. Before we end our talk session, we would like to have a group photo with all the guests.